So from now on we will start discussing manifolds, and to begin we would like to say that what are manifolds in the first place. So the manifolds are just generalizations of the familiar idea that we have about curves and surfaces. So we can say that manifolds are generalization of the idea of curves and surfaces. For example, let's say you have a curve in a 3D space, and let's say you parameterize that curve by a parameter u, where any point on that curve can be written as x of u, y of u, and z of u. And if you want to draw it, it looks something like this. Now, a curve and a surface, or the regular geometrical figure that we see in our everyday life, they are considered locally homeomorphic to some r or r squared. For example, if I take a very small region on this curve and I zoom in on this portion, then it locally looks like r. Okay? However, once I zoom out, I figure out that, oh, this is not the case globally. Okay? So this local homeomorphism enables us to give each point on a manifold a set of numbers that we will call local coordinates. So you can think of a manifold some sort of an abstract space, and that space will contain some points. And the very idea that this type of homeomorphisms are useful relies on the fact that this will enable us to develop calculus on manifolds in terms of the ordinary calculus that you see on any RM. That is the ordinary calculus that you do. Let's say you have a 2D space, x and y, and you do calculus over here, any sort of differentiation or integration of some function. This homeomorphic idea, the idea of the homeomorphism, will enable us to translate the calculus on manifolds in terms of the ordinary calculus. So first what we'll do is that we'll see some intuitive notion of what we are actually trying to do, and then we will move on to a more formal definition of what manifolds are. So to begin with, let's consider a unit sphere of radius 1. That's what we mean by an unit sphere, and this sphere is lying inside on R3. That is the three-dimensional real space. So if I draw the sphere, like this, any point on the surface of the sphere, this unit sphere, can be written as follows. Where theta and phi are just some coordinates, as you can see from this figure. This is phi, and this is theta. And you can even invert these expressions over here to find expressions for theta and phi. If you do that, this is fairly easy. You will have theta as tan inverse square root over x squared plus y squared divided by z, and phi would be equal to tan inverse y by x. Now you can even go further and choose different coordinates to represent the same point. Let's say you are dealing with this point, this cross mark over here. You can express them in terms of these coordinates x, y, z. You can even specify them in terms of theta and phi, or what you can do is that you can take stereographic projection, and that will result in the following coordinates. The stereographic coordinates, let's denote them with capital X and capital Y. They will be equal to some x divided by 1 minus z, and this will be y divided by 1 minus z. Okay, but one thing if you notice from all this is that you can take different coordinates to represent the same point. So the point is there independent of a coordinate system. It's just a matter of convenience how you want to define a coordinate system and how you want to express the point with the coordinate systems that you defined. So the main punchline over here is that point itself exists independently of its coordinates, and coordinates is just for the convenience of the observer or the user, and an observer or an user can choose any coordinates that he or she likes. And this arbitrariness of the coordinate choice is the thing that underlies the theory of manifolds. And what this means is that you can take any coordinate system and represent the same thing. So we say that the arbitrariness of the coordinate of choice underlies the theory of manifolds. This means, or this implies, that all coordinate systems are equally suitable for describing a single point or a single phenomena. However, we want to comment that the convenience of the coordinates will vary from situation to situation, but the end result should be independent of the coordinate system. But now let's revisit these coordinates, and if you do that you'll see something very interesting. What you'll see is that you cannot cover the whole surface of this this two sphere, that means the surface of the sphere, with a single coordinate system. And you might ask why cannot I do that? Well, first consider a path that lies when theta is equals to 0. That means you are moving on, let's say this is xy, so let's say you are moving on xy plane, and your phi can vary from 0 to 2 pi. So if you start from here, let's say, and let's say this is phi equals to 0, from here you can go around this great circle and you can come back at the same point. But when you come back at the same point, your phi value jumps from 2 pi to 0 on an instant, and that is not a smooth thing, right? Because if you start from this point, you are going from one value to over here to another value over here in a smooth manner, or so to say in a continuous manner. But once you reach the end, that means this point over here, your phi value jumps from 2 pi to 0. So there is a discontinuity. And moreover, if you continue to move past this point and then come over here again, at this point it is 2 pi plus some angle, right? However, when you initially started from phi equals to 0, you had some other value that was less than 2 pi, but now it's more than 2 pi. So this single point can have many coordinates. This is one thing. And even if you try to cover the sphere by saying that no, I really want to cover the sphere with these coordinates, you'll immediately realize from this expression is that when z is equals to 0, this theta, it doesn't even make any sense. Even though you might attempt to say that, oh, this is tan inverse some infinity which should give me pi by 2 or something, right? Because when cos pi by 2, that's 0, so it's 1 upon 0. But that's not the case, because at poles, not only you have this theta issue, but also at poles, that means this point, let's say this is the North Pole and this is the South Pole. At these 2 points, you don't even have any phi values. Why is that? Just look at this expression over here. It only contains x and y. But what are the values of x and y at the North Pole and the South Pole? It only has some z coordinates, right? So you have at the North Pole, let's say phi of n. If you want to compute the phi of n, you'll have a tan inverse 0 by 0 expression, and we don't know how to do it, right? So it is not possible to cover the entire surface of the sphere with just a single coordinate system. And also, when we talked about this great circle over here, we saw that 2 nearby points can have different coordinates, and they vary by a large number. So this is not wanted. This is not something we want. So we reached to a conclusion that we cannot label the points on the sphere with a single coordinate system, so that the following conditions are satisfied. So let me write it down. So we reach to a conclusion that for the sphere that we're talking about, we can't label all the points with a single coordinate system. Such that the following conditions are satisfied. The first condition that we were not able to satisfy with a single coordinate is that the nearby points always have nearby coordinates. What we mean by that? By nearby coordinates, we mean that if you have a point, let's say A, and there is a point B that is very close to A, then if the coordinate of the point A is x mu, B should be x plus epsilon mu, and this is a very small thing, a very small parameter. You can say it like that. So that's what we mean by nearby coordinates. And then the second condition that we saw that we were not able to satisfy is that every point has unique coordinates. So how do we get around it? Well, this is where the idea of covering the surface of the sphere with many local coordinate comes in. So what we can do is that we can choose infinitely many ways to introduce coordinates that satisfy these two requirements that we just wrote down, and when we do that, we do it in such a way that any two of these local coordinates will have some overlapping region. And by introducing two or more overlapping coordinate system, each covering a part of the sphere whose points are labeled so that the conditions that we failed to satisfy in the first place now get satisfied. So what I mean is that, let's say this is the sphere, but now instead of using a global coordinate system like before, we use small patches like this. Let's say this is one coordinate system, and let's say this is another coordinate system, and then I can have another coordinate system, and these are the overlapping regions. And we do it in such a way that we will always have these overlapping regions, and all the points on the sphere will be contained inside these overlapping regions. If we can do that, then we will satisfy these two conditions that we were failed to satisfy initially. So we write that if we cover S2 with infinitely many local coordinate systems, and introduce two or more overlapping coordinate systems, each covering a part of a sphere whose point to be labeled such that the following conditions hold. 1. Nearby points have nearby coordinates in at least one coordinate system. And number two is that every point has a unique coordinate in each system that contains it. Every point has unique coordinates in each system that contains it. So these are the two conditions that we can satisfy by introducing all these very small local coordinates. And if we go back to the example of the sphere, what we can do to cover all the points on the sphere is that we may introduce two stereographic coordinates on S2, and since we had trouble with the North Pole and the South Pole, what we can do is that we can introduce one for the North Pole, one projection from the North Pole and the other from the South Pole. Okay, and we need one last, or so to say an extra condition on this coordinate system, and that condition is that if two coordinate systems overlap, that means their intersection is non-zero, or so to say it's not null, they are related to each other in a sufficiently smooth way. And why do we need the third condition? Well, without this condition, a differentiable function, let's say this is some space, this is L1, a local coordinate, let's say A, and this is another local coordinate, let's say B, and this is the overlapping region. Now let's say in this overlapping region we have some function, okay? Because if I can define coordinates for different points, let's say I join them and make a function out of it. Now the third condition tells you that if they overlap, then this A and B, this thing, or so to say these two charts are related to each other in a very smooth way. Now, as I was saying that I can construct a function in this overlapping region. If these two are not related to each other in a smooth way, what will happen is that, or what might happen is that, if a function, let's say some f of x, which lies in this common region, it might be differentiable in A, but it might not be differentiable in B. So that won't make any sense. So that's why we require this third condition. And to develop the theory of manifolds, we need these three conditions inside our head. And before I move to the formal definition of a manifold, I want to comment that in most texts or whenever you have an introduction on manifolds, the very first thing you see is that we call manifolds are some space or generalization of spaces that locally look flat, or so to say they locally look like Euclidean spaces. So what does that mean? Well, let's say this is some arbitrary m-dimensional object. We don't yet know what this is, but if I take a very small portion of it and zoom in, this small portion will look like a flat surface. or a 2D Euclidean space. Think of the sphere. If you take any region on the sphere, let's say this is a very small region. Again, by local we mean very, very, very small. That's what it's meant by local. And again, you zoom in, you get a 2D space out of it, or 2D Euclidean space. But now let's take a look at another intuitive example. Let's say you have a 2D space. Okay, you already have a flat 2D space, but now what you do, you put some rod, or I don't know, introduce some string or an extra dimension. Is this a manifold? Or if you take any small portion of it, will it look like a 2D space? No, because if you just take this part over here that contains this rod like thing, you'll realize you cannot go from, let's say this is point A to a point B in a smooth manner. So this will not be a manifold. So intuitively, what we say is that intuitively manifolds are locally flat. Also, to say manifolds are objects that look like Euclidean space. And it doesn't have to be two-dimensional, not necessarily. It can be m-dimensional, where m is some integer number. And all of this will be more clear when we talk about the formal definition of manifolds.